Hi everyone and welcome to the ninth lecture of the tree series. In this lecture, I'll be explaining the problem counting paths. The problem says, you're given a tree consisting of n nodes and m paths in the tree. Your task is to calculate for each node the number of paths containing that node. This is the tree and these are the queries. Now for this tree, for the path 1 and 3, let's firstly write all the nodes. For the path 1 to 3, the nodes in the path are first node and the third node, right? So these will get an increment. Now the second path is 2 and from 2 to 5. Now this is the path. So the second node would get an increment, the first node would get an increment, the third node, and finally the fifth node. Right. Now the third path is from 1 to 4. This one, the first node would get an increment, the third one would get one, the fourth one, right? So the final answer becomes 3 for the first node, 1 for the second node, 3 for the third node, and 1 for last two nodes. Right. So the brute force approach would be, for each of these queries, we can call the DFS upon one of the endpoints and until it finds the second endpoint, and all the nodes in the particular path would get an increment of 1. But we know that the time complexity for DFS is big O of n, and the queries are queue, let's say. This would become too slow and won't work, obviously, and we need a more efficient solution to solve the problem. Now we will be using binary lifting in this problem and the concept of LCA. Now I explained the concept of LCA using binary lifting in the 7th lecture, and this will be a continuation of that. Now let's say I have this tree and my query is 10 and 14. Right. Now we know that there is only one simple path between any 2 points, any 2 nodes in a tree, and that would pass through the LCA. And the LCA of 10 and 14 is 7. Right. So this would be the path between the 2 nodes. Now I want an increment firstly on 10 and 14, and I also want an increment for all the ancestors of 10 until we hit the LCA. Right. So 9 would get 1, the LCA would get 1. Similarly for 14, 12 would get 1, and 7 already has 1, right? Now we want this increment for this particular path. Now let's say also we don't want the increment for this path in any of these nodes, right? The parents of 7 or any other nodes. Now let's see how a DFS can help us do this. So firstly, let's see, we are calling a DFS on the first node. This would go to the third node and ask for the total counts from all of his children, right? Now we know that a path should not contribute in the count of a particular node if that node is above its LCA, right? Or which does not fall in its path. So now for this, let's say 3 calls the DFS on 7 now, and 7 would call it upon 9. Now 9 gets the increment from 10, so it adds 1 plus 1. 7 gets it from 9, and 7 calls it upon 12. 12 gets it from 14, and 7 gets it from 12. Now 7 becomes plus 2. 3 gets it from plus 2, and 1 gets it from 3, right? It becomes plus 2. Now we can see two problems here. Firstly, the LCA is getting incremented twice for this particular path, right? This is the first problem with this approach. Secondly, nodes above the LCA are also getting incremented, right? Let's see how we can get rid of both of these problems. Firstly, for this, whenever we are taking the query, we know that the LCA of both of these nodes is getting an extra 1 due to this particular path. So what we can do is, when we are setting the increments for these particular nodes initially, we can decrement the count of the LCA by -1, right? So When we get the plus 1 for both of these, we can set the 7 as -1, right? And also we know that the finally, due to this path, 7 will get a plus 1 count, but we don't want this plus 1 to transfer to the third node, right? What we can do for this is, when we are setting the initial values for all these three nodes, which is plus 1 for 10, plus 1 for 14, and -1 for 7, can also set a -1 for the parent of the LCA, right? Now let's see what the increment for the count would be if we call the DFS upon the first node. Now first would call it upon third will call it upon 7, 7 for 9, 9 will get a plus 1 from 10. Now 9 will give the plus 1 to 7, and 7 will become 0 for now. Now 7 will call the DFS on the 12th node, and 12 will get the plus 1 from 14, and it will give it to 7, right? And all these four nodes, the count becomes 1, and for 7 also it becomes 1, right? From this, now the 7th node transfers to the third node, increments by 1, and it becomes 0. Now 3 transfers to 0 to the first node, right? So from this particular path, all the increments are correct, and this approach will work for any number of queries. Now the code for the LCA part will be the same as the previous problem and the problem before that. The only change would be in the query processing part, and finally we will call a DFS upon the first node to calculate the final counts for all of these nodes. So let's look at the code now. Firstly, this is an array of vectors. This is the ancestor array. This is the depth array, and E will be storing the answer for all the nodes. Now this is the pre-processing function like the previous problem. This is the DFS to calculate the depths, right, to find the LCA. This is the LCA function like the previous problem. This DFS2 function calculates the final answer for all of the nodes. So we visit all the children of the particular node. Firstly call the DFS upon that node and add the value of that child to this node, right? The value of the count of this node. Now this is the input part. Firstly we call the pre-processing function on the first node with parent as 0. Then we call the DFS function to find the depths with the initial depth as 0, so initial parent as 0 and initial depth as 1. Now for each of the query, we firstly find the LCA, then we increment the count of A and B, and we decrement the count of the LCA, and then if the ancestor of the LCA exists, we also decrement for that. Finally we call a DFS to find a solution, and then we print it, right? That's it. Now make sure you subscribe and share this video. Thank you for watching.